Now I'm not muted. Sorry about that. My name is Josh. I'm tuning in from Morrison Planetarium, actually from my home office. But we are joined here by Dr. J.R. Skok for one of our Friday Cosmic Conversations. So, Dr. Skok, how are things?
Things are great. We excited about this Mars mission that's coming up. We're about halfway on our way to Mars. So we're looking forward to taking a preview of the mission to come. And if you happen to get outside on the night sky, you have Mars that's very bright. We're just about 3 weeks past about every 2 years, the close approach. So that's usually the midway in between where we launch a mission to Mars and where it lands, which is due next February. So, I'm always a little happier when we can see Mars nice and bright in the night sky. A lot of really beautiful astrophotography, amateur astrophotography was taken from around the world, showing the beautiful features of the planet as it came close. And every day our robots, not only the American, but also a Chinese and a UAE mission are all on their way to go and explore Mars in the next few months. So whenever that's happening, I'm very excited about life.
So if folks walked outside and they look opposite the setting sun, what should they look for that tells them they're looking at Mars?
So it's going to be just a pretty bright reddish, star. It's going to look like a star, a lot brighter than most of them, and has a reddish tint. Most likely the brightest red thing that you'll find pretty high up in the sky, opposite of the sun, will be Mars these days. So we are flying into it.
We just flew to Mars, probably a bit faster than our spacecraft are going to get there, right?
That's a bit. It took about 8 months to fly there when NASA launches.
Would make for a pretty long show. Okay, so looking down at Mars, can you tell us a little bit about your expertise and what makes you so interested in Mars?
Yeah, I've been a fan of Mars from my earliest ages. When I was 4, my mother painted glow-in-the-dark stars of the autumn sky on my ceiling. So every night since I was 4, I stared up at the autumn stars. So that kind of affected my brain, and started doing Mars research when I first started high school, doing crater counts to understand the weathering rates of volcanoes. In college, I worked on the Mars exploration rovers and started doing spectral studies for research as I worked on my PhD to understand the volcanic evolution. Did a lot of landing site analysis, looked at the different landing sites that we eventually selected for the Curiosity rover back in 2012 in the process to pick among the best places on Mars. And I worked a lot on figuring out where we want to land the Perseverance rover that's currently on its way. So I've done, mostly looking at spectral studies, looking at the minerals and how the mineral history of Mars can tell us about the geological history, about where volcanoes erupted, what does that mean for the kind of heat interior of the planet, looking at alteration minerals, where water was once present, looking at hot springs and how that might be able to preserve evidence of life. So exploring a lot of the planet, figuring out where we might want to go to unlock its secrets.
So just before we dive in, and I think we want to go visit the planned landing site, a question we always get about Mars is why the red color, and what does that have to do with its composition?
Yeah, so Mars is a very dry place, and it has a lot of volcanic materials. On Earth, you have a lot of the primary rocks of Earth are very iron rich. It's a very common mineral it's a common element that's formed when stars explode. And on Earth, we get rid of a bit of iron by kind of repeatedly melting, and that creates like the granites that make up a lot of the continents. On Mars, you never had that kind of remelting process, so a lot of the surface rocks have this very abundant primary element of iron. And as Mars rusts in very minor amounts of oxygen in the atmosphere, that creates this kind of rusted ferric iron dust that kind of coats the surface of Mars. So a lot of that is kind of very superficial. So once you start brushing away, you get to more kind of standard colors. So you get to like the blacks and the browns and the different colors that you would get on minerals on Earth. But except for this kind of dust that's on the very top bit of Mars and all throughout the atmosphere, and that's what makes it red when you kind of look at it in the large scale.
So we've got an ability to show folks some higher resolution imagery on Mars, but it's going to make Mars look a little weird. Can you tell us about some of the CTX imagery?
Yeah, so the Mars Reconnaissance orbiter, it's an orbiter I worked on a different instrument on for a lot of my research. It flew around, took a lot of really high resolution images of Mars, down to like 25 centimeter per pixel. It's like super resolution images. And then a slightly larger viewpoint, about like a couple meters per pixel, is the CTX, context imager, that allows us to do pretty good mapping of Mars that covers a lot of the surface area. So these are the CTX kind of context images that we still didn't have the bandwidth to cover like the entire planet. And due to changing weather and dust storms and all that, we don't have quite complete coverage in this resolution, even though we cover most of the planet. So these are just basically a mosaic of hundreds and hundreds of these CTX strips, just basically images as the orbiter flies over, images as a strip of data, and then put together to create this kind of mosaic of strips that give us much higher resolution of the planet, but still enough context to see most of the planet.
That's awesome. So if folks are interested, I realized I said all of this while I was muted. My apologies. We're doing our show today in OpenSpace. OpenSpace is a free software, and if it's one you would like to check out and fly around Mars just like I'm doing right now, all you got to do is head to the openspaceproject.com, and you can actually find out some really cool things about what's going on in Mars. We had a couple questions pop up. Is there polar ice on Mars that could be terraformed into an atmosphere? And has there been an atmosphere in the past?
So there's a couple of good questions in there, and a lot of
complex
pieces. So the general consensus is that if we look, or like, we'll find that out in a moment, where we're going for this Perseverance rover, it's going to be the Jezero Basin Lake. And so this is an area that at one time had a lake of water. We know it had running water, otherwise we wouldn't get the rocks we're seeing today. And the current atmosphere of Mars is just too thin for water to really flow across the surface. So the fact that we see so much water evidence in old rocks on Mars, we think that it must have had a much thicker atmosphere early on in history. So that's, I think, the second part of the question. There was a much thicker atmosphere on Mars early, maybe the first 500 million years of the surface of the history of the planet. And then as the planet kind of cooled off, it lost its magnetosphere and started losing atmosphere, gas to outer space. And eventually we have the pressure, a very thin pressure atmosphere we have today. And so you don't have stable water. So that's the second part of how we kind of got a very thin atmosphere today from evidence of having a much thicker one in the past. There's still a lot of questions about how thick it was, how warm it was. All those are still opening and evolving, but it's really hard to explain all the features we see on Mars without having a much more significantly thick atmosphere in the deep past. So the second part, or I guess the first part of the question, is polar ice on Mars. Yes, we see that on both poles. It's seasonal. There's a permanent throughout all the year CO2 ice polar caps that we're going to, I think, the North Polar Cap in a moment. It might be on the dark bit.
You can turn off the nighttime to give us a better view.
So yeah, CO2 is there, I think, all the time. And then seasonal, or I guess, switch that. You have CO2 that kind of comes in and out with the seasons. So when it's the winter time, that expands rapidly. And in addition to that, we also have a water ice polar cap. So some of this is water ice, some of this is CO2 ice, depending on the season and the relative amounts. So it definitely has polar ice of both CO2 and water ice. And on top of the, and if we're talking about, yeah, so we also see this kind of change. We see seasonal effects where there is a bit of atmospheric change in pressure as this kind of comes out on a seasonal level. I guess the idea here is if we were to take all of the CO2 that we see and as ice and put that into the atmosphere, would it be something that's terraformed? The numbers I've seen are kind of skeptical about that, that in order to have an atmosphere that, at least when we say terraformed, it's like formed for Earth to have like R1 atmospheric pressure. I think there's just not a lot of not enough molecules that I'm aware of that we've counted on our kind of very still rough inventories that would be able to be liberated from the ice that we've melted or that we've mapped that we could then put into the atmosphere. Caveats are if we're doing that large of geoengineering, there's other options, right? Like if we churn all the carbon that's stuck into the rocks into the atmosphere, that one would get us a much higher inventory. If we were to bring in, water ice from comets or other bodies and put them to Mars and put them in the atmosphere, if we're talking big scale terraforming,
that was a pretty big project.
It would be, but that's a way to get a lot more just molecules of gas into the atmosphere if that was the goal. So terraforming is a tough project to do, to put that simply. So there is polar ice. Terraforming is another level of challenge.
So you'd mentioned Jezero before, and we've got our context imagery up. Can you tell us a little bit about what makes this place something worth sending a spacecraft to?
Yeah, so since kind of a little biased by our experience on Earth, where we find water on Earth, we find life. And so if we're looking for, this led to this kind of concept on Mars in the 20 years ago now. If we find evidence of water, we find that everywhere on Mars. So if you ever read the news about Mars, every couple months we find water on Mars, water on Mars. So we found water on Mars, and now we want to see if life happened to be where the water was. And so the Jezero Crater, this has a couple of key factors. We know it has this delta stream where you see a river kind of flowing off of the kind of northern part of the crater there. You see these little river channels that came in, and then it creates this kind of fan of material. And the exact nature of this fan tells us that this isn't just like an alluvial fan where it kind of flows with water and then spreads out over a kind of dry desert. You see these in the western US all the time. But this one actually was deposited in a lake. It has very special topographies that only happen if you're depositing the sediments in a body of water. So this was a place that was once an active water-filled lake that then had water running into it and creating this. So the water is kind of what makes us think that, if life maps to water, this was a place to have water. So there may have been life in the system. So that's the first part that makes us interested in saying if there was life ever on Mars, this is a good place to go and see it was here. The second part is because it's a delta, this is basically a geological tool for preserving evidence of life. The way that the kind of sediments come in, they kind of capture whatever biological molecules happen to be there, and they preserve them really well. So if you are we're looking, so a lot of the big point of the Perseverance mission is to look for biosignatures, evidence of ancient life. And one of the top biosignature hunters on Earth is like the oil industry, right? All of oil is basically a big biosignature of ancient life on Earth. And one of the places they always go to on Earth is these ancient deltas. Ancient deltas all throughout the Earth, they captured these biomolecules from hundreds of millions of years ago. They then preserved them in sediments and allowed that to be not only captured, but then preserved for hundreds of millions of years. And on Earth, they were heated up enough to produce like the hydrocarbons that we then go and use for fuel. But that same process of capturing and preserving biological molecules, we're hoping happened here. So it's this mix of evidence of water plus its really good preservation ability is why this mission's going here to search for evidence of past life.
We had a couple comments pop up that I think are fascinating. I said Jezero, but would Jezero be more correct?
Most of the community calls it Jezero. I'm definitely not a speaker of Bosnian, so yeah, it means lake in that language, or just the comment says. So most, I think the way I've heard it pronounced is Jezero, but
astronomers are pretty famous for developing pronunciations for some objects too. So
but it's tomato, tomato, so like whatever one want to pronounce, it becomes.
I think I've got a little bit better resolution. You can really see that kind of river structure coming down in. And then I think if I zoom in, you can see that delta you were talking about. This is a really beautiful site. The topography is dramatic. I can see all these ridges off in the distance.
So if you ever been to like the Mississippi or Louisiana, like, or New Orleans, like this is just a couple hours down the road from there. Or the Mississippi's creating deltas like this. The Nile Delta, these are forming all over Earth now, wherever you have these big river channels and materials being deposited and preserved in them all the time. And eventually they then move up and down in the geological record. And so there's a lot of Earth understanding, a lot of history that we've studied on these on Earth to preserve, dinosaurs as well as micro biology. And we're hoping to bring that huge bit of knowledge from Earth to Mars to look for evidence of life as we now take a rover and slowly drive through here.
Well, before we get to the rover, one last question just about our kind of geology in the area. I guess Mars areology. Is there any possibility of there still being moisture, maybe mud or water underneath the surface of this delta?
Most understanding is that this is going to be pretty dry as far as anything that we consider water. We found a lot of hydrated silicates. So these are minerals where water is kind of bonded into the chemical structure. So when a geologist is talking about it, we see chemical water as part of the geological record, but we don't expect to get wet at all as we're driving around. And that's almost intentional too, as we start to select places on Mars. There's always a chance that if we were to go to a place that was actually had water, that it might have life today. So we try to generally avoid the possibility that we're going to like maybe infect a place with modern water on Mars, which whether or not they exist is still an open question, and there's debate on certain places that might have a possibility for that. But usually places that we want to explore now are places that would have had water billions of years ago and not a lot of chance of finding it today.
Okay, so trying to keep Mars safe from all the stuff we've brought with us from planet Earth.
Yeah.
So we're down on the surface now, or at least pretending to. What can you tell us about the upcoming mission, the rover itself, and some of the cool accoutrements we know it flew with?
Yeah, so the goal of this mission is to kind of take the next step. If you follow the history of Mars exploration, our first missions to land in the 70s, the Vikings, they just wanted to land. They wanted to see whether or not we'd see trees and large-scale features of life on the surface. They didn't find anything. It was just a desert, and we didn't go back for 20 years. So that kind of destroyed a lot of momentum. But then during looking at the data from that mission, we found all this evidence of water. We found outflow channels. We found we didn't quite find deltas like this yet because they weren't high enough resolution, but we found evidence of water all over the planet and enough interest to start to go back and look for more water. And so then we did in the 1995-96 area, we landed another kind of test rover, the Sojourner and Pathfinder missions to test whether or not we could actually land on the planet again. We landed, it worked well, and that led to the Mars exploration rovers, and they just wanted to find evidence of water, and they found abundant water in both the landing sites. So we know Mars had a very active water geologic past, but they didn't have the tools to actually look for life. If they, they could have been driven all over fossils, but they didn't quite have the tools to say this was that. So the next mission, the Curiosity mission, landed in 2012, and that was sent to laboratory. And that one went to another place at a possible lake, and they found possible organic molecules, I believe, and a number of other things. And that mission's still going on, trying to understand this big set of sedimentary layers. So that's still going. So the final results of that mission have not yet been written. So it's still building a story. But the idea is that if we realize that it's hard to actually confirm whether or not life exists in a molecular sample. And it turns out that we do not have the technology to send an instrument or even a couple instruments to Mars to say for certain whether or not this rock is a fossil or not. Given how old it is, given how different Mars life could be, there isn't really a mission we could send to Mars to say for sure, without any controversy, this was a fossil. So they kind of changed their process and went to kind of a sample return idea. So we go and send a mission to Mars, pick up a sample, bring it back, and then use the very best instruments on Earth to figure out whether or not it had a fossil. And so that's why we went to Jezero here. You can see this line. So we want to land kind of out in the where it says rover path there to the edge of the delta. We're going to land there and then drive around and try to find these samples, which we're going to collect little tubes, test tubes basically, to try and pick together a very, very carefully selected 100 grams of materials that we can then send another mission in the future, bring them back to it'll pick them up, launch them into Mars orbit, and then a third mission, because it's really hard to bring back materials from Mars, we'll pick it up, rendezvous from the orbit of Mars, and then bring that back to Earth. And the idea then is that by that time, we'll have many more years to figure out how to look for biosignatures in these materials and have the very best instruments that have ever been developed to look at it. And so between the very carefully collected samples and all the instruments on Earth, we're hoping to say, yes, this is a fossil. Mars had life. This is what we know about it. So that's a strategy that led us. So then we had to find out where is the best place, if we're going to invest all these billions of dollars and many, many years, where is the best place to find a bit of fossil on Mars? And we looked at hot spring sites. We looked at kind of deep crustal sites. And for a number of reasons, the scientific consensus is that this area, with its clear evidence of water, its really good depositional kind of fossilization process, as well as its kind of extended mission. So like here we'd try and find these kind of collected samples of whether or not life was preserved here. But once we start driving kind of down this route here, we see like the numbers 3, 4, and 5. We start to go from these kind of sedimentary layers, which are really good at collecting and preserving fossils, but kind of missing a bit of the context of how Mars formed, right? Because Mars planets, they have like their primary rocks, which then get weathered and turned into sedimentary rocks, and you lose a bit of that record of how Mars formed. So this is a great place for finding a kind of preservation collection of life on Mars, but it probably wouldn't be the rocks where life may have been forming. For that, we'd want to do this extended mission where we kind of go up this pathway into the rim of the crater and beyond to kind of see where the deep rocks of Mars were back when it was warm and wet and had the energy for microbes deep in the crust to kind of form. And then hopefully by then, we'll collect samples that have life in the delta and then go explore the environment that those life examples would have formed in, as well as really looking at what an early planet looks like. Some of these rocks in the rims of this crater are the oldest rocks in the solar system, or oldest planetary rocks in the solar system. If you wanted the oldest rocks possible, you go to a meteorite. They're often very primary. They haven't seen water. They haven't seen a planet. On Earth, most things are relatively young to a geologist. Earth is 4.5 billion years old. Most rocks are under 1 billion years old. There's a few crystals from Australia that are around 4.1 billion. There's a few rocks around 3.8 billion, but that first 500 million years of Earth history is basically gone. Whereas Mars, that first 500 years makes up much of the planet. And so we can go not only understand early history of Mars, but possibly what the very earliest rocks on Earth were by going up into the rim and beyond for this mission. So those are what we're hoping to find here.
So we're doing all of this work to try and understand Mars rocks. What makes a Mars rock on Earth so very special?
So why do we want to pick this collection of samples? So one little step back is a Mars rock on Earth, more generally, is not actually that rare. We have several hundred kilograms of Mars meteorites that were blasted off the surface of Mars in impacts and traveled through space and fallen on Earth. So you can go out and buy for a couple $100 a little speck of a rock that formed on Mars. But the problem with that is, we can learn a lot about Mars from those samples. We learn about its volcanic history, about when it was formed. But the problem is we learn what Mars wants to tell us. Only the very strongest and youngest and most robust rocks survive that process. Like, it's really hard to be blasted off a planet, travel through space, and happen to be found and survive on Earth. So, So there's a lot of selection process there. So any of these soft sediments that might preserve fossils are obliterated and just don't survive. So, a Mars rock on Earth isn't as rare as you might think it would be, but the very carefully selected, very kind of delicate samples that we're trying to put here, where not only do we might preserve these evidence of life, but we also have the context. So when we have these asteroids, these meteorites from Mars, we don't know where on the planet they're coming from. We've done some analysis to say, oh, we think they're from there, but we really can't tie them back to the Mars to really understand the context. Here, we're going to have very good preservation and very fine context to know these samples tell us about this area, which tells us about Mars. So that is what this whole mission is about, is tying these samples to a specific spot on Mars to then tell us, not only did it have life, but how did it form, how did it evolve, and then applying that to all planets. What was the first 500 million years on an Earth-like planet actually look like? And this might lead us back to, if we understand that piece of Earth history, or that piece of Mars history, which then tells us about early Earth history, we might have a much better idea about where life on Earth came from. So this, when we talk about the goals of this mission, like, we want to find life on Mars because that's interesting, but in the end, we might end up learning a bit more about where we came from. How does a planet form the cells, the first early process of life that led to us? And that's, for a lot of scientists, like that's like the main question is like, why are we here? Why did this planet give rise to the wonders of life? So we're hoping to dive deep into that question, partially with this mission.
Now, one quick question I always like to ask whenever we're looking at the surface of another world, can you give us some kind of context? Like if you, JR, were to set down at the alluvial fan in Jezero Crater, Jezero, and start walking up the channel.
It's a delta, not a alluvial fan. We know that this was, specifically we're going here because it was laying in water.
Delta, okay. My apologies. So from this delta, going up, hiking up the inflow area, how long would it take you to get, I don't know, a good distance up? Is this something you could traverse in a day, a week, a month?
Some of it depends on how often you stop, how many rocks. So this is, if you're a very healthy hiker, I think I want it's a few somewhere between a handful and maybe a dozen kilometers to kind of go from across the delta and into this rim. So it's the sort of thing that a dedicated hiker, if there was a trail, could do, cover a lot of it in a day. If you had a car, you could ram over it really. A car and a good road, this is not that huge. If you're a rover making the first ever drive through unknown terrains, and you got to make sure you're not going to fall off cliffs, maybe you could do a few hundred meters in a day. If you find a flat stretch and you're comfortable with your rover driving and all that, a few hundred meters in a day is like a good day's trek. If you're stopping every 5 feet because you get excited by a new sample, then you're going to go much, much slower. So it really depends on how much science. That was a big issue for the two Mars rovers, exploration rovers, is do you stop and do science, or you just drive? And that's going to be a big battle here, because we need to, before the mission, whatever it ends, we never know when a mission's going to end, right? It might die from an engineering problem, it might fall off a cliff, it might get hit by a meteorite. Anything could happen. And before that happens, it needs to have these samples kind of collected and put somewhere safe, so the next mission can do its part. So it's probably going to play it a little safe until it gets that, and then go on more adventures.
Sounds like a good approach. Before we leave this kind of idea, I think there's two ideas tied in closely to it. One of the parts of this rover might not be doing any roving, though, right? It might be zooming. Yep,
we have the first ever drone on another planet, a little helicopter. I think it's called Ingenuity, possibly. That is this little softball-sized helicopter thing. And Mars has a much thinner atmosphere than we have on Earth, so it takes much bigger propellers. They do bring up much less weight. So flying on Mars is not easy, but they have big vacuum chambers at NASA that basically brought it down to Mars atmospheric thickness and proven that this thing can actually take up or fly. And so they were able to package this up and build it and test it. And so hopefully fly it around Mars. Hopefully, I believe there's possibly a camera there that will then take aerial photos to help with route planning. So that's always a question. Like when you're driving, you can only really want to drive as far as you can see. So you add a bit of satellite images and then look in the distance. But if you have aerial images to say, oh, this place is clear of hazards, that will really help both scout out samples where you want to go to sample, as well as driving quickly.
That's wonderful. The other question came from our chat on YouTube. Is it better to send a lot of small rovers many places, or one big mission to a single spot? What determines an approach and why?
Yeah, so that is an important question. And it kind of comes down a bit to the type of science you want to do. On Mars, it's still an unknown planet. We've sent 7-ish missions there, and mostly to safe spots, places that we know we can land and then do something. But there's as much surface area, the dry area of Mars, which is the whole planet, as the dry area on Earth. They're pretty close. So, imagine understanding all of Earth by landing in the 7 safest spots to land, the 7 flat spots. You're going to miss all the cool mountains and interesting things that this planet has to offer. And that's kind of what happens on Mars. And so that's a big question that we ask. So if we want to know what's going on Mars, you want to go as many places as you can, because then they each have different terrains. But the kind of counter argument is a small rover is harder to do things. So if we want to bring good instruments to study what we're going to see there, it's really hard to do that on a small mission. So once we start getting more complicated than the science we want to do, we want to get more sampling processing power. That's going to just be a bigger, more involved mission. And on top of that, landing is hard. So a simple mission, landing, you want to land somewhere safe. So there's a bit more weight and retro rockets and software needed if we're going to land in a more complicated area, and that just kind of makes things a little bit bigger. So if you just want to explore the planet, many missions are great. If you want to really advance science, that kind of pushes you towards bigger or more involved instruments and mission concepts, which takes you to larger missions at fewer places. So that's a bit of the trade-off. And there's always there's only so much money to study space for whatever NASA budget, and we always have this issue, right? Like if we send 100 small missions to Mars, that's 100 small missions that we're not exploring the moon or exploring other places. So there's always this trade-off of just going to Mars versus other things. And so if we are going to Mars, we really want to take science to the next level, and that also kind of pushes us towards bigger, more particularly developed missions. So in order to keep the next mission to Mars kind of high on NASA's priority, it does tend to be a more complicated, more ambitious mission. So that's usually kind of the trade-offs that go into picking what will be the next one to Mars.
Speaking of this kind of implementation stage, you're coming up with the idea. Are there any challenges that crop up that you weren't expecting? Laura asked.
In what sense? Like why are we doing a sample return versus other?
Let's say on the Curiosity mission, even in design or in implementation, something that happened that was really unexpected on the drawing board.
So I know one of the big challenges for Curiosity is you often one of the challenges for going to Mars is that we're always learning more. So every day that we kind of don't know where we're going, we have more science to understand. So especially during the era that we were landing, deciding where to go for Curiosity, we had the Mars Reconnaissance Orbiter that just kind of started operating in 2007, 2008, and that was just bringing back so much data that the scientists were figuring out, where are the most interesting geology, where's the most interesting sites. And so basically every day that you don't decide where you want to go, we have more data, more images, more understanding about the relative benefits. And so you have, so scientists want to wait every day possible to have a better idea of where we want to go, but engineers need to build way before, they have to design the mission way before. So they start being a little generalist, right? They want to say, okay, we'll build a mission that can go and land anywhere, and then the scientists can pick any of those places they want to go. And so, but the problem is you kind of either have to design a very kind of clunky general mission that can land anywhere on Mars, or you kind of very save money by shaving off the engineering challenges. So for example, a big issue on the Curiosity rover is they have lubrication for the wheels, and they eventually turned out that the lubrication that they originally wanted to use it wouldn't work in colder areas. So if you went too far away from the poles, even though it had a nuclear power generator so it could operate without any sunlight, if it got too cold, it would stop basically being able to drive. And so they eventually decided that the extra cost it would take to make the engineer cold or make the mission cold enabled isn't really worth the possible science you might get from colder areas. So they said, okay, you can't go north or south of this line for temperature reasons. You're stuck in this bubble around the equator, and we're just not going to engineer beyond that. So that's always the challenge, is picking, engineers want to know what they're building for so they can build the most efficient mission. Scientists always want to wait as far as they can in order to have the most possible information. So that's the balance that they're always fighting.
Can imagine some grumpy meetings. But Corey asked, have any meteorites impacted any recent missions? Is that a concern?
That's not a no, that's usually not a concern. We always talk about when you're walking around on Earth, right? Like you could be hit by a meteorite any day, and I think it happened about once that I know of. But there's one woman who was sitting in her living room, and a meteorite came through and hit off the roof and glanced off her years ago, and that was the closest we've had to a human impact. So there's a very little chance that a meteorite will hit you. but we have found meteorites on the surface just sitting there. So we know they fall at any moment. It's much more likely that a software challenge will happen, some little bug of code that tells the rover to like look away and forgets to wake it up. That's much more common than a meteorite happening. But you know, it's you never know what is going to kill you on a given day. And there's no repair people there to go and fix your rover. So even the smallest issue might end of mission. So that's always a concern, is you drive like there is no tomorrow.
So Corey asked, if you had to pick your favorite Martian moon, would you pick Phobos or Deimos?
Oh, they're so great as a pair. Personally, I like Phobos a bit more. It's a little bigger and has a little more features to it. It makes a little bit better of a eclipse because it's just bigger and covers up more of that, you know, the sun ellipse. So, yeah, I would have, if I'm forced to pick, you know, it's like your children. You never want to pick one or the other, but Phobos would probably have to get my vote.
I'm glad we're in agreement. I think Phobos is fascinating, especially the low density part. Okay, I think we are caught up on questions. Anything else you'd like to share with our audience?
Get ready for an amazing mission. You know, one of the issues with missions is it's exciting to see them launch, and then there's not much happening because it's in space. And then there's a big excitement when it lands, but you know, that's just the beginning of it. Right? You know, you get the first images, it's like, ooh, a new place on Mars, but we know nothing about it really. It takes time. So, you know, mark your calendars for an exciting NASA blitz of public relations and media back in February. You know, I think we all need exciting off-planet news, I'm sure by then.
Take it. Yeah, absolutely.
So get excited to be, you know, get ready to explore a whole new place on Mars. It's really one of the most interesting places that we've ever been there. So that's going to be exciting. And then get ready for a long process of just learning new cool things, seeing the best images ever taken of another planet. A lot of debate will be going on about sampling that rock or that rock, and probably that debate will not probably hit the major news, but NASA will be covering it. So you know, a lot of cool stuff will be coming out of this mission as they have figure out which samples to return back to Mars. And you know, this is your you know, tax money is going to be investing in this mission, so these are going to be a bit of your samples, right? They're going to belong to all of us. So feel excited that these are going to be, you know, human samples that we're bringing back that belong to us all.
Happy to contribute. That's so cool. So I know on our Morrison Planetarium Facebook page, we will for sure be sharing exciting information about the missions to Mars as they become available. But JR, is there any place else people should be tuning in to find out more?
NASA has like I think a Mars a website portal that's usually really active with beautiful images and mission updates. I haven't quite seen the one that's going to be built full. Like usually when they launch the mission, it's going to be packed full of images. But I'm certain that this will have some beautiful media, videos, hopefully some awesome drone photos as this thing's flying around. That. So just check out NASA, and they're really good at communicating the beauty of other planets. So check out the NASA.gov and the Mars channels that it has.
Well, thank you so much, JR, for joining us. It is a real pleasure to talk to you as always, and we look forward to more collaboration in the future.
Yeah, likewise. Thank you for having me.
So everyone at home, thank you for tuning in. We really appreciate you coming week after week for our cosmic conversations. They're fun for us to make. We hope that you enjoy watching them. If you liked what you saw on Open Space, be sure to check it out. On Morrison Planetarium Facebook page, we'll be continuing to update with more information until our dome reopens. But thank you all for joining us. And no matter where you find yourself today, stay home, stay happy, stay healthy, and have a wonderful rest of your day. Thanks again.
Bye.